Okay, so the topic we have today is called linear programming. It's also called linear optimization. It's a branch of mathematics that's used to do maximization and minimization problems. So one of the classic examples where this started was during World War II. Soviet mathematicians were using math to optimize certain expenses, certain things. So for example, if you were the army, just think about it. If you're the Soviet army in World War II, what do you want to minimize? Your casualties. So if you're that you want to minimize, they would like to minimize Soviet casualties. Okay, there's also a list of things they might want to maximize. What would they like to maximize? What is it? Yeah, so in this particular war, they would like to maximize German casualties. Okay, so you went straight to the blood and guts of it. There's other things. What are other things if I'm an army I want to minimize? Cost. Okay, I would like to minimize my cost. Okay, okay. What are other things that I want to minimize or maximize? Pardon me? Okay, so that brings up another question. So maximize soldiers. I mean, in ideal world, I would like to have an infinite number of soldiers with an infinite number of guns, and I can beat any army, right? Okay. Or just suppose I'm Apple. If I'm Apple, I would like to sell how many iPhones? An infinite number of iPhones. Can Apple sell an infinite number of iPhones? No, because what do they have that keeps them from doing that? What's the English word? They have what? Budget. They have constraints. Okay, so you've got maximize and minimize, but there are constraints that we need to think about. So go back to the Soviet army. What are things that constrain the Soviet army in this problem? Do they have an infinite number of soldiers? No. So the constraints are, so the number of soldiers. What are other constraints they have? Number of weapons, okay? So this is, in a nutshell, the kind of problem we're going to be working with, okay? I'm going to have constraints, and my goal is going to be to try to maximize or minimize something. So let's think of back to the case of Apple. Apple, to maximize their profit, would sell an infinite number of iPhones, but they can't sell an infinite number of iPhones because there are constraints. What kind of constraints would Apple have? What is it? So budget, but they also have like a factory. Can a factory produce an infinite number of iPhones? No, because they have a finite number of employees. They have a finite number of hours in a day, a finite number of machines, okay? So that's the kind of problem that we're going to be dealing with. It's not going to be all war and blood and guts. It's going to be more boring stuff like ice cream cones or, so things that are happier than war. So what we need to do in this particular case is graphically, so these are word problems that have a heavy graphical component. So I want to make sure that your graphing skills are where they need to be for solving these problems. So you need to make sure you can graph a line that's given in standard form. This is standard form right here. AX plus BY equals C. There are two other forms for graph. Let's talk about another form. So there's another form that you knew for a line that's called slope-intercept. What is slope-intercept form? Y equal, mx plus b. I'm not going to spend a whole lot. We're not going to reteach this, so this is stuff that you should know. Slope-intercept form, because this tells me the slope of this line is what? M. What is b? The y-intercept. The y-intercept is where my line crosses what? The y-axis, okay? You get the y-intercept by setting x equal to what number? 0. You get the x-intercept by setting y equal to 0, okay? Never forget that. X-intercept, y is 0. Y-intercept, x is 0, okay? So slope-intercept is a form of the line that you might see as well. But graphing a line that's in standard form is pretty straightforward. The way I'm going to do that, I'm just going to pick a couple points. If I look at this, if x were 0, okay, look at this equation. If x is 0, what is y? Did I hear 3? Okay. If y is 0, what is x? 6. Okay, does everyone see how I did that? All I did was, if you substitute x equals 0, you're trying to solve for y equal 12. That means y is equal to 3. If you're trying to substitute a y equals 0, that means that 2x equal 12, so x equal 6, okay? So most of the lines we're going to graph in this section are going to be given in standard form, and you'll be asked to graph them using this. So now what do I do with these two things? I use this to graph the line. What axis is this? This is what axis? This is x. This is y, okay? Now, here's the other skill you're going to need. I give you a lot of these grids in this unit with no numbers on them. Okay, don't do that to confuse you, but this problem, it's because these problems scale differently, okay? So if I'm going to look at my x-axis, what's the smallest number? My x-axis needs to scale from 0 to 6, right? My y-axis needs to scale from what? 0 to 3. So if I want to try to use as much of this graph as I can, you know, what you don't want is your graph to be like, there it is, I'm done, okay? That's sort of hard to look at. So you want to try to use as much of this as you can. So let's just use this. If I need to go from 0 to 6 in x, so if I went 1, 2, 3, 4, that wouldn't get me. So let's just say if I spread it out like this, if that's 0, 1, 2, 3, 4, 5, 6, okay? That way I'm using a good portion of the graph. So every other line I numbered it, okay? Now, if I need to go from 0 to 3 in y, I could go 1, 2, 3. I could spread that one out. Or you could say, you know, I'm going to do it just like I did the x's. So I could go 1, every other one, 2, 3, that's 3, 4, 5, something like that. So I've spread that out as well. And I'm going to need to take a little bit of a... Okay, so now I'm ready to graph this line. This line starts at 0, 3. Which is right here, and it goes to 6, 0, which is right there, okay? And let's draw a line right here. So my line is going to go from here to here. And there we go. Now the other skill in this section, you try to be as neat as you can, maybe use a straight edge. The other suggestion that I will give, you know, if you have two colors of pens or color pencils, it would be very helpful in this unit because I only graph one line here, but what if I were to graph 3 lines here? The color can be very helpful. So anyway, I'm just throwing that out there as a helpful skill because that's what you'll see me doing here on the board. Okay, this is Algebra 1 stuff. You got that? This is where you say yes, okay? Let's take a look at another one. Now, we graphed a line. We graphed a linear equality. Now, the other skill you got to be able to graph a linear inequality, okay? What's the difference in this problem and the one we just saw? Yeah, the other one said 2x plus 4y equal 12. This is 2x plus 4y greater than or equal to 12. How do you graph an inequality? What does a graph of a linear inequality look like? Right. Yeah, so Kendall's right on. So this was the graph I graphed the line. So my answer was the line. If I have an inequality, my answer is not a line, but it's a what? Somebody said shade. It's a region. It's a shaded region. So here I'm saying, what are all the points that 2x plus 4y equal 12? That's the line. Now I'm asking, what are all the points that 2x plus 4y is greater than 12? So I'm asking for a region. So here, the first steps, what you need to do first is graph the line. So I'm going to need to graph the line 2x plus 4y equal 12. Now, is this line going to be a dotted line or a solid line? Solid because it says greater than or equal to. So solid line, do the same thing. When x is 0, y is 3. When y is 0, x is 6. We talked about that. So we will graph this same line. So this is 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5. So we will graph the same line that went from 0, 3 to 6, 0. Okay. Now, what do I do next? Yeah, I'm either going to shade above this line or below this line. What do you think I'm going to do? Yeah. So, and these, so typically what you're asked to do is pick a test point. What's the point that they typically let you pick? What's the easiest number to pick? 0, 0. If you were to plug in a 0 and a 0 here, is 0 greater than or equal to 12? No. So 0 is not part of the solution. So if 0 is not part of the solution, where do I shade? Above the line. But in all of these problems, if this is 2x plus 4y equal 12, the greater than says where are the numbers that are greater than? It's going to be all of this, okay? So that is my solution, okay? Hey guys, what's the difference in this problem? I don't have to do it. Yeah, a couple of things. It doesn't have the underline and it's doing what? Yeah. So it's what? 0, 3, 0, 6. This line is a dotted line, okay? So in this one, I'm going to shade 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. I'm going through 0, 3, and 6, 0. I'm going to draw this line. And this is not a solid line. This is what? Dotted line. Everyone see why it's a dotted line? Because it says less than, not less than or equal to. Where do you think I will shade for this one? Below. Okay. So this is the answer for this one. Now typically, I'm drawing the first quadrant. Typically, when you graph this in your other classes, you might see this and you're shading, if this were the XY axis, you're shading a lot. But all of these problems we're going to be dealing with in linear programming, I'm dealing with the XY coordinate, all of those being positive, okay? So that's why I'm setting these problems up a little bit like that. Okay, so here, graphing a line, that's a skill you got to have. Knowing whether it's dotted or solid, knowing whether you use shade or above or below. These are skills that need to be in place before we get to any of the word problems. Now, how do we graph a system of linear equalities? A system of linear equalities means instead of one, I've got several to deal with, okay? So this is the other thing that all of these word problems are going to set up, a system of inequalities. So I got 4 conditions here. These, if we talked back to our example of the Soviet Army, these are the constraints, okay? So I'm going to be able to graph the constraints before I do the optimization. So look at these 4 constraints that you have. Most every problem we deal with is going to have X and Y being positive numbers. Because if I'm dealing with stuff like hours in a day, if I'm dealing with, the number of iPhones a company can make, those are what kind of numbers? Positive numbers. So all of our word problems deal with positive. X is greater than 0, okay? So if I look at here, this is my x-axis, this is my y-axis, this is 0, 0 down here. If x is greater than 0, I'm over here. If y is greater than 0, I'm up here. So I'm only dealing with x and y as being positive, okay? So those are sort of the trivial constraints. Now let's look at the other 2 constraints. 2x plus 3y is less than 18, less than or equal to 18. The first step before I graph the region is I have to graph the what? Starts with an L. The line, okay? So how do I graph this line? If x is 0, y is 6. If y is 0, x is, see you guys? And then over here, if x is 0, y is 4. If y is 0, x is 4. So this is enough to graph the two lines that I have. So the first one I need to graph, and I shade, where am I going to shade when I graph the line? I'll shade where? Below it, right? So I need to graph 0, 6, and 9, 0. So if I look at my x-axis, how high up do I need to go from points 0 to 4, 0 to 9? My x-axis needs to go from where? 0 to 9. My y-axis needs to go from what? 0 to 6. So let's just make sure I've got that scaled correctly. What I would do is says 0 to 9, that's close to 10. So I'm just going to say, well, let's just, if we did it like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I need to go 0 to 6. That's pretty close to 10. I'm going to scale it the same way, every other one. 1, 2, 3, 4, 5, 6, 7, 8, and so forth. So the first line, I'm going to need to graph 0, 6, and 9, 0. So let's do this line in blue. 0, 6, and 9, 0. Okay. Now it's just playing connect the dot. So connect these two dots together, and a straight edge will be a wonderful thing if you're doing this at home. Okay. Okay, there's the line. And what does this tell me? Where do I need to shade? I need to shade below this line. Okay, so this one I'm shading below. When I graph the next line, where will I shade? This one above. Okay. So shading below that line. So if I shade below that line, okay, we have shaded below that line. Now let's graph the next line. The next line needs to go through what points? 0, 4, and 4, 0. So 0, 4, and 4, 0. Connect those dots. I try not to cuss in class, but if it happens this semester, it will be when I'm graphing one of these things, fighting with this smartboard. Where do I shade relative to this line? Above. So this one is going to be like this. Okay. So what's the solution to this inequality? Anyone? Which of these shaded areas is the solution? The middle. So like what had to happen is what is below the blue line and above the red line. So this is my solution right here. So this is, why is that not writing? That's my solution, okay? So all I did in the first step, I had one inequality, okay? This one I had two. So you have to pay attention to, it was shading below the blue line, above the red line. What do they have in common is that middle section. So this is my solution. Now in our word problems, this is going to be your constraints. You know, this is the number of Soviet soldiers, you know, or the number of weapons you have. These are your constraints. Okay, think about it. If you're, suppose you're Apple, you know, and you're trying to sell iPhones. Okay, and this is your profit. You want your profit to be as what? As high as possible. Okay. What if these are my constraints? Okay, I want the profit to be as high as possible, but still meet these conditions. That's what we're after. Okay, so graphically, you got to be able to graph this region, and then we'll talk about how to maximize and minimize these constraints. Okay, this is what we just did. Okay, I just wrote it out for you. You did it by hand. This is showing it graphically. Okay, Now, the other skill you're going to need is when you look at this feasible region, you're going to need to identify each of these, we call these vertices. So this region right here that we just graphed is called the feasible region. It means that if I've got a solution, it has to be in this shaded area. And then these endpoints are the vertices, okay? Let's go back to the example we just did. How do I identify these vertices? What are, let's just write them down. What are the vertices of this feasible region? What's this point right here? 90. Up here? 0.6. And what's this one? 0.4. And the last one is what? 4.0. Okay. So you'll need the skill of graphing the region and then identifying each of these vertex points. Okay. So in this particular one, I've got the feasible region and we just identified the vertices. I'm not going to write that down again. So that's graphing the feasible region. Okay, so those are my constraints. Now I need to be able to maximize something. Okay, so if those are my constraints with regards to, say, producing iPhones, I want to maximize profit. So I might have a function that represents this. So if you've got a device on you, you can grab that, or you can just certainly watch here. But what I want to show you is how this happens. So let me make this a little bit larger. In your book, there's a URL there. So if you want to play with this on your own, this URL will do what I'm about to do right here. Okay, this is what we just graphed a moment ago. Okay, so you saw us graph this region, the feasible region right here. Now, what you see over here, this black line, suppose this is maximizing profits. Okay, I want profits to be as high as I can. Okay, so look over here. If this is my profit, does the profit meet my constraints? No. Okay, so this is like telling Apple, create 1 million iPhones and sell 1 million iPhones, or infinite number of iPhones. Well, it doesn't meet the constraints. I want this profit line, if I'm talking about profit, I want to be as high as possible and still do what? Meet the constraints. So what has to happen is, right now this line is not meeting the constraints. To meet the constraints, I need to move this line, okay? So look at what's happening here. So this is the first time I am meeting the constraint, right? Okay. So look at where the profit line is. So the profit, let me move it down just a bit. I can get it. So you can see, okay. I'm meeting the constraint, and look at where my profit line hits the y-axis, okay? Is that a better profit than over here? I'm still meeting the constraints, but what's happening to my profit? It's going down, okay? Here I'm meeting the constraint. Here I'm meeting the constraint. Here I'm meeting the constraint. What was the best place for this profit line? Where was the best? This was the best case it was, okay? So what happened is, if this is profit and I want to meet these constraints, this is where I want to do it, okay? So that's what we're going to be after graphically. Now, let's switch gears. Suppose this is not profit. Suppose this is the cost. If you're in business, you want your cost to be what? The least. You want to minimize cost. So pretend like this is the cost now. Right now, is this where I want my cost to be? Where would I want my cost to end up? Yeah, so where's the lowest point? That appears to be right here, okay? So if I'm minimizing the cost, this is going to be my answer, okay? So what's going to happen in this section is you're going to have to graph a feasible region, and then I'm going to give you something called an objective function. That is, you need to maximize or minimize something, and you're going to need to do that by looking at, you can do it graphically, but really what happens is, if you look at it in this case, as I move this line, it was the four vertices where something happened, okay? So whatever happens here is in between. The extremes are either going to be at one of the points. This was the highest point, and this was the lowest point. So if I can test this function at all 4 of these boundary points, then I know where it's maximized or minimized. Now, before I go on, let's just real quick, let's change something here. Let's change this function right here, this line. So look at this line right now. If I want to maximize this, where does it hit its maximum? There, not there, okay? So all that happened to this line, what was the change in this line? It's what changed? Slope. It's slope, that's the key. So it's the slope of this line that deals with which of these points is going to be the maximum. Which is going to be the minimum for this one? Not this one, but this one, okay? So it changes. So you never know until you test this function which of these is going to be the maximum, which of these is going to be the minimum, okay? So let's get back to where we were. So we're going to test this. The vertices that we just found in that region, help me, what were they? They were, was it 9, 0? 0, 6, and then 4, 0, and 0, 4. Okay. So here's the function. This is my objective function that I'm trying to maximize, okay? So all you need to do here is evaluate this function at this point. So what is 20 times 9 plus 15 times 0? What is that number? Let's go with 180. What is 20 times 0 plus 15 times 6? That is 90. What is 20 times 4 plus 15 times 0? That is 80. And what is 20 times 0 plus 15 times 4? That is 60. So, which of these points represents a maximum? Yeah. So this one, I have a maximum at 9, 0. What is my maximum value? Come on, guys. 180. I have a maximum value of 180 at the point 9, 0. I have a minimum value of what? Minimum value of 60 at what point? At 0, 4. Okay. Now, in the context of what's going to happen the next time I see you, we'll be talking about iPhones or chairs or buses or something. So the word problem will have context. This is just the math behind it. Okay. So what were the steps? You have to be able to graph a line, graph a system of inequalities, look at a feasible region, find the vertexes, and then I'm going to give you some function and ask you to maximize it or minimize it. And so there we go. So what we just did a moment ago, you saw this. We could see graphically when that line moved, you could see visually that this was the maximum point. So the maximum point was at what? What was this point? 9, 0? The objective function was maximized at 9, 0. What was the maximum value? It was 180. And this thing was minimized at what? Which one? 0, 4. And the minimum value was it 60? Let me go through there. So I want to maximize this objective function, okay, subject to these constraints, okay? So let's talk through, what do I need to do? Right, first of all, do I do anything to start out with the function? What do I need to do first? The constraints, okay? So I need to graph these constraints to come up with my, what's the word name for that region? My feasible region, okay? Figure out the feasible region, and then once I figure that, I need to figure out all of the what in that region. What kind of points? The vertices. Once I find all the vertices, I plug them into what? The objective function, and determine, what am I trying to do here? Maximize or minimize? This one says maximize, okay? So I'm going to graph the feasible region, figure out all the vertices, plug those vertices into the objective function. So what have I got to graph here? All of these are pretty much going to have x and y greater than or equals 0. So this is x and this is y. And I've only given you part of the graph where x and y are greater than or equal to 0. That part's good. So we got half of the constraints here. Now I've got two other constraints. And what you will see me do is I'm going to use color. So I've got 2x plus y is less than or equal to 7. That's one thing I need to graph. And the other one is y minus x greater than or equal to 1. So let's go back to this first one, and I'm going to do something like this every time I do this. What are the easiest numbers in the world to pick? 0. If x is 0, when I'm going to graph the line, what would y have to be? 7. If y is 0, what would x have to be? Yeah, 7 halves or 3.5. Okay. And over here, I've got x and y. If y, let's just do, if x is 0, what is y? 1. And if y is 0, what is x? Yeah, -1, okay? So this one, I'm drawing the line. That's outside my feasible region because x and y are positive, but it's okay. I'll be able to graph it, okay? So I need to scale up to what in my x-axis? X-axis needs to scale from 0 to 3.5, and then y goes from 0 to 7. So why don't I do it this way? Those numbers feel pretty close. Let me just go every other one. So let's just do 1, 2, 3, 4, 5, 6, 7, and then the y-axis 1, 2, 3, 4, 5, 6, 7. Okay, let's take care of the blue line first. The blue line goes through what, 0, 7, and then what's the other point it goes through? 3.50. So that is right here. So I'm going to draw a line through that. Okay, that is my blue line. Now the red line goes through 0, 1, and what? -1, 0. So that's somewhere, looks like it'd be about right here. Now, if I don't like that, well, that's sort of off the graph, okay? Why don't I pick another number? What would happen if x were, say, 3? If x is 3, okay, let's look at that. If y minus 3 equal 1, then y is equal to what? 4. Okay, so the point 3, 4 has to go through this. So let's try that. 3, 1, 2, 3, 4. This point right here has to go through the line. Okay, that gives me a better shot of drawing this. So I'm going to go from here to here. Oh, I'm doing a line. Now, what do I shade relative to the blue line? What do I shade what? Above or below are my choices. Below the blue line and what? Above the red line. Okay? Below the blue and above the red. So where is below the blue and above the red? Is it here? Is it here, here, here? What is it? Below the blue and above the red. Does everyone agree that's right here? Okay. I tend in these problems, I like to get to this point and just shade the region. If you shaded like everything that's below the blue and everything above the red, and look where they intersect. Sometimes the graph is a little bit messy, okay? So this is my feasible region. How many vertices are there? There's a vertex right there. There's one right there. Where's the other one? How many are there? There are 3 vertices to this feasible region, okay? So the next step would be to figure out what these vertices are, okay? So let's figure that out. Let's go, and this is what I look at. This is why I like color in these graphs. This is which line? This is which color? What color is this line? Blue. Okay, look at my blue. What do you think that point is right there? 0, 7. Okay, I got that vertex down. And then this one, this vertex is on my red line. Go to the red line. It's 0, 1. Okay. Now this gets a lot harder when you've got like 3 or 4 lines and the numbers are not easy like 0 and 1. So I've got this vertex, this vertex. What about this one here? Well, where do these lines meet? It looks like maybe 2.5. Maybe it's 2.5, 2. I don't know. I don't know how good your graph is. That's okay. I'm thinking it's 2.5, 2. Is that a good feeling? Do you think I grade on feeling? How do I figure out where these 2 lines intersect? Do math. There we go. Okay. As opposed to history. Okay. So here's where you guys are in luck. You got a TI Inspire. There are a couple ways of doing this. You are trying to figure out where these 2 lines intersect. Okay. If you were in Algebra 1, they may have taught you to do what? Solve this equation for y, and then do what? Plug that into the other equation. Solve that for x. You get x is 7, and then you substitute that in and get, or excuse me, you get x equal 2 and y equal 3. I'm not going to spend time with this, okay? This is something you did. So if you want to do substitution, you can do that. Now, you just took a test on something called what? Matrices, okay? You can look at this and say, you know, this is a matrix equation, okay? The answer to that is the inverse of this matrix times 7, 1, okay? You know how to do that, right? This will be, yeah, okay. Let's just do that method real quick. So it's 2, 1, 1, negative 1. So to solve that would be what? I would say, okay, I need to do the matrix 2 by 2 matrix. And that 2 by 2 matrix was 2, 1, 1, negative 1. So 2, 1, 1, negative 1. And then that matrix is multiplied by 7, 1. Not that matrix, but it's what? Its inverse is multiplied by another matrix. What's this matrix? Is a 2 by 1. Sorry. So times menu 7, 1, 1, 2 by 1 matrix, which was what, 7 and 1. So that, oh, did I do a mistake? Yeah, I typed something wrong. It's 2, 1, negative 1, 1. What did I do? Oh, yeah. What I did what I told you guys not to do is to enter this thing wrong. Negative 1, and so x is 2, y is 3. Okay, so what did we think when we first looked at it? We thought 2.5, 3. We were wrong, okay? So this is x equal 2, y equal 3. So this point right here, that point is 2, 3. Okay? Now, here's the other way to do it. And This is my favorite way to do it on the TI Inspire. It's what you see here, okay? So let's do it this way. Hopefully you'll like this one. Menu, algebra, solve system of linear equations. How many equations do I have? 2. How many variables? They are x and y. So this is good. What was that first equation? Come on, guys. What is it? 2x plus y equals 7. Okay? So 2x plus, was it y? Y. And where's the equal on here? Well, I'm graphing the line. 2y equals 7. Dad, what was another one? Was it x? Was it y minus x? Y minus x equal 1. Solve these equations for x and y. And what did I do wrong? What did I do? Oh, typo. It was 2x what plus y? 2x plus y, and that should be it. What am I doing here? Oh, sorry. If I recall this, you can always go back, recall, and now I get to edit it. So come right here. Two x plus y, so now I've got it correct. There we go. So what you can do in your calculator, how did I do that again? It was menu, algebra, solve system of linear equations, 2 variables. I just plug in the equation without the typos, and it solves for me and gives me the 0.23. Now, you can do however you want. Substitution, matrices, this is the quickest way of getting this done. And let's finish up this problem. So these problems are, what do you characterize these problems as being? What's an adjective to describe this problem that I'm doing? Long, would that describe it? Okay. So, what was my final answer? I wanted to do what? I wanted to maximize that function. What's my final step? I've got to plug these 3 points into that equation, okay? So I got to figure out, what are those points? 0, 7, and what was the other one? 0, 11, no, 0, 1, 0, 1, and 2, 3. Oh, that one's empty. Sorry. Okay. So guys, stay with me here to the end. X plus 2y. So this is going to be what? 0 plus 2 times 7. What is that? 14. At 0, 1, it's going to be 0 plus 2 times 1, which is 2. At the point 2, 3, it's going to be 2 plus 2 times 3. That's 2 plus 6, which is 8. Okay? Where's the maximum value? Right here. Okay? So this function, your maximum of 14 at 0, 7. Okay? So guys,